So today, finally, we will define what analytic stacks are. And in fact, it's not so difficult. So recall that we have this infinity category of analytic rings. So this was actually, as Dustin mentioned at one time, it's actually presentable infinity category. So Dustin proved that it has all colimits, and actually it's generated by a set worth of analytic rings under all colimits. And so we can make the following definition. An analytic stack is an accessible function so this word accessible is just there to deal with some set theoretic issues. From analytic rings, or if you want, Fn analytic spaces up towards Honeyman. So recall, yeah, so this word accessible here, the definition, there will be a condition in just a second. So this means that it commutes with kappa filtered colimits for sufficiently large tuplets. It's such a function such that so it satisfies sheaf conditions. And the precise way I want to phrase the sheaf conditions as follows. For any sheaf hypercover. Sorry. Go again. So assume you have some unspec A and then some hypercover unspec A bullets. For which V of A and Y up the streak is isomorphic to the streak limit of the derived categories of all these terms. Also, X of A maps isomorphically to the limit of X. So, by the way, I write unspec where Dustin just wrote spec. I don't know. I don't think we've settled on a final notation. Just not to get it confused with the usual spec, let me write unspec. So this is some form of descent that's somewhat strictly between.
So can I ask just a minor technical question concerning the notion of hypercover? So in usual algebraic geometry, do you hear me? No, is it okay? There is the green they hear.
I don't know. Ask him if he hears.
Do you hear me?
Yes, I hear you. Yes.
Okay. So let us consider the case in usual algebraic geometry when, for example, you have like a FPQC topology or something like this, and then there could be two meanings of FPQC hypercover. So one meaning is that the map from X0 to X and the map from Xn to coskeleton are FPQC. And the other meaning is that they are coverings for the FPQC topology, which is, so sometimes it causes some concern what is the meaning. So in our context, you use the strict meaning, I suppose, that everything, I mean, you...
Yeah, so I want all maps should be streakable, but then there is no difference between, like if it's defined by a streakable cover, then it's already a cover because of the descent condition.
Okay, so here it is satisfied that if a streakable map is dominated by
a streakable cover, then it's already a streakable cover. So
okay, thank you.
Right, and I also need to say that it commutes with finite disjoint union or finite products. So commuting with finite products, including the empty product. And geometrically, this just means that X evaluated on a disjoint union is like the product. Okay, so this condition is so this defines, I mean, up to such theoretic issues. And it's isotopos that's somewhere between three sheaves and three fiber sheaves. So for streak sheaves, you would only consider some Čech nerves of covers. And those would, by definition of what a streak cover is, always satisfy this condition. So for Čech nerves of streak covers, you always have this condition. So it's always a streak sheaf. And for streak hypersheaves, you would ask this condition for all streak hypercovers, whether or not they satisfy this condition. But we definitely want to our derived category to satisfy to be some have this property. So we need to restrict the class of hypercovers which we allow. All right. And let me just state this as a remark and not prove it. So, so sheafification of an accessible pre-sheaf is accessible. So this is the analog of the theorem of Waterhouse for the HPC topology. So in particular, this means that you can actually form co-limits in this category, because a priori form the co-limit in the category of the pre-sheaves, so just the functors from analytics to anima. And this is still an accessible functor. But then you need to enforce the strong sheaf condition, so you need to sheafify, and you can check that it's preserves the set theoretic famous condition. All right. So examples or remarks. So for any, first of all, for any analytic ring, we can look at the functor which takes, we can define unspec A as a functor which takes any B to the maps from A to B.
So again, I have a small technical question concerning the sheafification, which I believe you mean sheafification, making it satisfying this precise condition that is not the Schrick sheaf and not Schrick hypersheaf, but just intermediate condition.
Yes.
But then, in order to construct this sheafification, you need for the pullback. It seems that you need to know like that the pullback of this kind of hypercover satisfying the condition on the derived category is also this kind of hypercover.
So you need to know that the pullback of such a thing is against such a thing. But again, this follows from the same argument. So this is actually equivalent to to d of a being the co-limit along the lower street maps of the d of the VA bullets. Where the co-limit is taken in this word of presentable infinity categories. And this is a condition that base changes because these derived categories base change in PRL. And well, base change always commutes co-limits.
So you use all of this. Okay. And this was discussed in a previous talk, this equivalence.
Yeah, this was what Dustin discussed. I mean, this is all this magic about PRL.
Okay, and then you use it is the tensor product when you base change. Okay.
All right. So first of all, you have all the affine objects. So for any analytic ring A, you can consider on spec A, which takes any B to the homes from A to B. Claim this commutes with this satisfies all these properties actually already, so you don't have to shiftify. So it certainly commutes with products, right? Because you're coming into something here. And then you need to check this this descent condition here. And now maybe I shouldn't have called this A, but so now you have a hypercover. No, yeah. You have a hypercover some B with some B bullets, and then you somehow want to map to B. But so in particular, you want to map like in particular B is like the limit of the. So shrink descent implies star descent again. So in particular, A would be the limit of the A bullets. And so if you map to all the B bullets, then you actually map to B, and also on the level of the derived categories, you actually map to the derived category of B again because it's the limit of the. So yeah, so this is an step. So analytic rings up, and yeah, I mean just by basically only this is a fully faithful functor. So the analytic rings up, so this embeds fully faithfully into analytic stacks. Okay, so obviously on stack is my notation for the infinity category of these stacks. And actually, this accessibility condition is precisely the condition that you're a small co-limit of objects in the essential image. Let me not. Just try this. So when you look at our notes on like condensed sets, and we do play a similar game there when you have like a full category of condensed sets and sets. So ways to think about them, either just as being both via small co-limits from profinite sets or being such accessible functors. All right. Okay, so what is this category of analytic stacks? Well, for any analytic ring, there's an object, which is some of the analytic spectrum of this. All the others are built by some gluing procedure, by some co-limiter of those the affine objects. And the way to think about this hypercover condition is somehow that it tells you ways in which you're allowed to glue things. So if you somehow have such a hypercover satisfying this condition, then the co-limit of this simplicial diagram there of these unspec A bullets would be the same thing as the unspec of A.
No idea. So the co-limit is over infinity. Okay. Yeah, co-limit over.
Okay. And so as will maybe become clearer later in the lecture today, so we want to impose we want to have this very general topology because it means that analytic stacks which a priori have seem completely different because they have completely different presentations. So they are completely written in a priori completely different ways as a co-limit of affine guys. Often there is like a geometric picture that they should secretly be the same object. And in order to say that they're really the same guy, you somehow need to chiefly find a rather strong topology so somehow makes them the same thing. All right. So okay. So next example is similar that this is in sometimes generalizing algebraic geometry.
Different colimits because of the strong nature of the Grundig.
Okay.
You have a question?
Oh, sorry. No, it was
just the small in number 2, the small co-limit of objects, in which category it is taken?
Here?
Yes. In analytic stack or in no, before stack. Limit in before the stack condition. Just
it would also be co-limit before the stack condition because actually sufficiently filtered co-limits preserve this condition there because there's a countable limit condition only ever.
okay.
So if you take omega 1 filtered co-limits, they will always preserve this sheaf condition. But no, but you certainly have to take the co-limit in here because like even if you glue just the few affines to the P1 or something like this, like even the P1 wouldn't be the co-limit of. What would it? Sorry.
Probably because
no, sorry. I know. Yeah, I think the two things are equivalent, but okay.
Accessible should be some condition, preliminary condition.
Yeah, so a different way to think about this is that you can also like put a cutoff condition on your analytic rings that there's some kappa small for some kappa. And then you can just consider such stacks defined just on kappa small analytic rings. And then there's a way to extend them to like the full class, but some left-hand extension. And then, yeah, I think arguing this way, you can probably show that.
Okay, okay.
Yeah. All right. So there is a functor from like derived schemes. The derived schemes, they also, of course, embed into like sheaves for the descendable topology. And then we can go to specs. Taking in particular like any spec A for usual ring A to on spec A. Then you take the condensed ring, which is really just discrete, and you allow all condensed modules of this. And if you want, you can also, like as Justin discussed, you can basically put the FPQC topology in here, except you have to do this funny countability assumption. So I'm doing with omega 1 FPQC. So basically, like any FPQC stack can also be mapped to a stack. And there's really not much to show here, right? I mean, you definitely just have to functor on rings. And then you just have to show that whenever you have a descendable cover, then it goes to such a streak cover, but that's basically by definition. And again, you could also use this funny thing between sheaves and hypersheaves here in the descendable topology here if you wanted to. Right. Right. Maybe I can mention that theorem that is actually fully faithful on
What
drives.
is it for you? A sheet of view is a it's like a fullback where you
This actually uses Tanaka duality. It uses Bloch's Tanaka duality.
Do you need QCQS?
I think he can get rid of this because he can certainly reduce to the quasi-compact case, and then there's this argument of over that he can write as a limit of quasi-separated things.
You can how do you reduce to the quasi-compact?
Well, you can certainly, if you want to understand the homes from X to Y, you can cover X by, but you can assume X is quasi-compact, but then that's quasi-compact Y, so you can definitely assume they're quasi-compact.
Oh yeah. Okay.
And then there's this other argument that you can make the equivalence relation quasi-compact. So I think you can reduce the QCQS. All right, so you have some algebraic geometry sitting in there. Next, you have Analytic spaces sitting in there. And the function Analytic spaces. That makes sense. Which, well, these are good from affinoid ones, so these are bar A plus. That makes like when you talk about Sheafy Analytic spaces, you always assume that this is Sheafy, and so what I'm saying now, let me also assume this because otherwise I would run into some longer discussion about exactly what I want to do. And so I can just send this to the unspec of the analytic ring A plus solids. So note that this way we get a different functor. You actually get two different functors. So there are actually two ways to embed schemes into Analytic spaces.
What is to discuss with?
So you can take a spec A. You can also match this to bar A comma Z, also bar A comma A. And then further.
There's a question in the chat, Peter.
There's a question.
It says for derived schemes, you're mapping the trivial analytic ring structure?
Exactly. Yeah. So here I'm currently using trivial analytic ring structure.
Right. No solid or anything.
And so you can either now take this further and look at A modules and solid Z modules, or you can look at relatively solid A modules. And so now and if you wanted to, you could put a derived here, suitably formulated, and then also put a derived here. So then there are like three functors from schemes or derived schemes to analytic stacks. Either with the trivial analytic ring structure, or with the one induced from the integers, from the solid integers, or with this relative solid. All of them are like fully faithful embeddings. And all of them are kind of relevant to what we're doing. So you actually have to kind of start to differentiate between these different incarnations of a scheme. And particularly like the one embedding where the notions that we use for analytic stacks actually match the usual notions for schemes is actually this relatively solid one. So Dustin introduced some notions of like closed emergence, open emergence, and so on. And they had the peculiar feature that, like, for example, any map of affines becomes a proper map here, and like in particular, like open emergence become closed emergence here, which sounds very weird. If you use this other embedding instead with a relatively solid structure, then open embeddings go to open embeddings, as you would maybe rather expect.
And the first one is still another one. The AZ is still another one.
Yeah.
So you have 3 ways to put schemes.
Well, more than 3 really. I mean, the one AZ is just you take that one and you base change it to solid Z, so that you could base change to anything. And yeah, well, I'm saying the most basic one is that one, and then the first one up top there with AZ solid,
Yeah,
is just gotten by base changing that one from Z with the
Right.
trivial.
So let me just write down what Dustin's just explaining.
Oh, he can hear us. Yeah.
The green thing is open, and then it's also I don't.
Right. So one thing to notice that the first of these is a functor from 3. And then you base change from the unspec of just the integers to unspec of these solids. And I mean, this immediately suggests a generalization. For any analytic ring A, you can then say even derive schemes over A. They can be mapped to analytic stacks over A. But just using, well, maybe you should write a triangle, the underlying condensed. Sorry, the triangle of the point. So you take if you have an analytic ring, then it has an underlying condensed ring, which has an underlying just discrete ring, and you can look at schemes over there. So for example, I don't know, you might have the complex numbers with their gaseous analytic ring structure, and then you can just consider usual schemes over the usual complex numbers as just a field. And those map to analytic stacks over there by just using the previous functor and then base changing. And so, right. Whenever you have an analytic ring over A, there's and again, this is actually fully faithful.
Yeah, you mentioned something slightly puzzling about derived Adek or derived Huber pairs.
Yeah.
So what does it mean? Does it mean that you have a derived ring with A plus in pi 0 and it is and all the pi
I just
are
numbered it because I didn't want to go into it here right now. Yes, one can define a version, like some derived notion of like Huber ring, but I really don't want to do it right now.
Ah, okay.
And like for each functor, I wanted to indicate to what extent we know that this is fully faithful. So this functor is definitely fully faithful on affines because then it reduces to maps of rings, and we know that Huber rings embed fully faithful in the analytic rings. And so here we know that it's fully faithful under some quasi-projectivity assumption. or speakable definition for the projective. We don't know a fully phased Morris result, basically because we don't know a good version of Tanaka duality for Analytic spaces.
I don't know if this is also like if it's worth warning that in contrast to the scheme case, the Analytic space, the functor doesn't commute with pullbacks, or
right. So actually, if you restrict to like Tate Analytic spaces or music Analytic spaces, or however you want to call them, then there it behaves as expected. As long as you stay in the Schiffe case, otherwise you might have to make things derived. Yeah, but then there's this peculiar feature that, like on the right-hand side, if you take a file product of affine analytic stacks, it's always just the usual corresponds to the tensor product of rings. This is not true in Analytic spaces. So in Analytic space, you can have a fiber product of affinoid space that's not itself affinoid anymore. So there's some subtlety there that can actually be explained in a very nice way in our formalism, in a sense that it's instead some yeah, let me not do it here. All right, so then you can also do, like this is non-Archimedean geometry, you can also do geometry with the or Archimedean fields, like real or complex. And for example, you can have complex analytic spaces mapped to analytic stacks. And now there's some work over, for example, the gaseous complex numbers. And how can this be described? So the one problem is that usually, like in complex analytic geometry, people don't really tell you what an affine space is. But they could. So any complex analytic space can always be written as some kind of union of what we call complex Stein subsets. So these are things that really very much behave like affine objects. So what is a complex Stein? So for example, the vanishing locus of some ideal inside just a polydisk. So these are tuples of complex numbers, all of which absolute values as most one.
So functions holomorphic in the neighborhood.
And right, so what we endow this with is the algebra function we put on such a K is an over-converted holomorphic function. So we endow it with O of K dagger, which is a co-limit over all U, which strictly contains this complex subset K of the holomorphic functions on U. And then it is a theorem from the 70s or 80s that, at least in this case where you're really close to the polydisk, this is Noetherian algebra. It is excellent, and if it's actually a manifold, it's regular, and so on. So it has all the nicest properties you could ever hope for. And like, if you want to talk about like coherent sheaves on X, then you can really just talk about like for any complex Stein subset, you give just a finitely generated module over this Noetherian ring, and they can give you space change.
So as far as I remember, for some book on complex analytic geometry, so there is a small subtlety which is usually not very important, but still for the Noetherianity and so on, you could have an ideal such that the number of connected components of the zero locus is infinite, and this is bad for Noetherianity. So there is some
Yes,
finite condition.
That's why I said that for things which are actually of this form, that they're risky close and pointless, there it is Noetherian.
What?
There's a slightly more general, like compact Stein would allow something like profinite subsets in a Poides, and this wouldn't be Noetherian. But if it's a risky closed subset of a Poides, it is in a Noetherian algebra.
Because it is a polydix and not arbitrary compact. Okay. Yeah, I remember that it was for another other compact. Yeah, okay.
Right, but I mean, if you like there is this way of looking at complex analytic geometry where there's really a very close analog of the notion of an affinoid subset, and everything you really have Noetherian algebra, and everything is really very, very similar to how you do it in rigid geometry. And so you would send that similarly to like the co-limit, which is actually again just union over all such k and x of the unspec of this algebra, endowed with like the gaseous analytic ring structure induced from the complex notice. And yeah, I mean, like algebras of holomorphic functions, they have a natural topology, like uniform convergence on compact subsets. So this also has a natural topology. You could also define it directly into condensed setting, whatever. It's the so-called dual nuclear Fréchet space. And again, this is fully faithful on like symphotic.
You take this with which analytic ring structure? Okay.
Oh, just so you view it as an algebra in the say gaseous C theory.
Yes.
And then you just take the induced analytic ring structure. So you just check on the underlying.
And so this defines a condensed ring, which is actually an algebra with complex numbers, obviously. And because it's a dual nuclear Fréchet, it's actually gaseous. And so you can just induce up the gaseous analytic structure from the complex numbers to here.
Sorry, not every dual nuclear Fréchet is gaseous, right? But
what? They are. It's not nuclear as a gaseous. It's certainly gaseous.
oh yeah, okay, sorry. Yeah.
I mean, these are actually even nuclear in the gaseous here, but
yeah.
What is quasi-projective? No, but there it should be fully faithful. No. If it's not fully faithful, you don't have
It should be fully faithful in general. It's just tough to prove.
No, but a point, it should give a map. I mean, the map of analytic, it should give a map of underlying topological spaces.
Yeah, that's what you need to prove. Yeah.
What?
Yeah, that needs to be proved. Yeah.
And what is quasi-projective?
It means it's like admits some immersion into projective space. So maybe like an open subset of a closed.
So what's the question?
Oh,
what is quasi-projective?
Some locally closed immersion into projective space.
So it's closed in an open.
It's closed in an open subset of projective space. Maybe before I go to the next example, there's actually nothing much special about using like complex manifolds or mixed fields here. I mean, you can do similar definitions work for similar definitions. It works also in the real analytic case. For real analytic manifolds. Or actually also for smooths, or you could also, I don't know, take any kind of CK or just C0, so topological manifolds.
You take that's the ring of CK functions.
Well, the ring is again a slightly peculiar thing that you take, like, still do this co-limit of functions on neighborhoods. And overconvergent continuous functions is a kind of awkward notion, but it makes sense. That's what you should do. And in each of those cases, you can actually decide whether you want to take real or complex valued functions, and they give you two different functors, where one is just the base change of the other. So one you can make an analytic stack of the reals, and you can base change it to the complex numbers if you want to.
Can you use the gases here or what?
It doesn't really matter.
No.
You should do something at least as complete as the caches.
All right. And now comes like a more funny example. So I mean, this is like showing that all the usual series like of algebraic geometry and of analytic geometries that are known, and maybe okay. So we should also at some point discuss Berkovich spaces. They would also have a natural functor. They map into our framework, and well, in any of those frameworks, you could also directly define some notion of stack. So there could be, you can imagine many possible notions of a complex analytic stack by starting with complex analytic spaces and endowing them with any Grothendieck topology you could think of, maybe just open covers. And then also stacks for that topology would map to analytic stack, just because any open covers in particular is sweepable cover. All right. So
Covers which go to shrinkable.
But now comes a slightly more clear example, which is relating it back to what we started with, namely condensed sets, or because everything has become a stack, let's take condensed anima. And as always, take the light ones. So those actually, they also map to analytic sets. How does that work? So this takes any, and actually you could even go to like, you don't really have to go analytic for this. You can just this would even work for just schemes. So in particular, like here there's something condensed. On the right, there's also something condensed, namely like the analytic rings, there were condensed rings and so on. But we're actually not using this condensed structure here. It really comes from discrete objects here. How does it work? So if you have a light profinite set, then you can just map this to the spectrum of its continuous functions. Right. So if S was a finite set, this would just be a finite disjoint union of copies of spec Z. In general, S is the limit of finite sets, and then similarly, this is the limit of these affine schemes. And so then we can map this further to the spectrum of those continuous functions. So you can do that. And then here's the reason that we chose this really funny version of between sheaves and hypersheaves. So condensed anima, they are by definition hypersheaves. Of anima on light profinite sets for the Grothendieck topology of that we always use. And so to get this functor, you have to show that if you have any hypercover here of a light profinite set by light profinite sets, then it goes to something for which you enforce descent here. And it definitely goes to a hypercover. And so then there's a small thing you have to check that it actually is a descent condition on the derived category holds. Basically, the argument that faithfully flat maps satisfy descent, it just also proves this statement. Countably presented faithfully flat maps. Yeah, so I should say that here it's the lightness condition is again important because It's always true that if you have a surjective map of profinite sets, then if you look at the corresponding map of continuous functions, well, it's always flat for any map of profinite set, and it's surjective if and only it's spacefully flat. But we need a descendable map for our business, and so we only know that counted represented faithfully flat maps are descendable, which is another reason that we have this Leibniz assumption.
What is the question?
Right. Right. So yeah, so here's a remark. So there are different ways of embedding schemes into analytic stacks, and now there are also different ways of embedding something like topological manifolds into analytic stacks over the complex or real numbers, say. So either you can do this thing where you use the algebra of continuous real valued functions to do this, or you can treat a topological manifold purely as a topological space or get fully faithful into condensed sets, and then go like from condensed sets to analytic stacks. This gives you a different thing, which is actually defined over the integers, right? Because this analytic stack, yeah, is just a integer value function here. So these are analytic stacks defined over the integers. So these are completely different incarnations of a topological manifold as an analytic stack. But there's actually, again, a map between them. So let's consider the following example. So you can take the two sphere as a topological space, and then treat it as a topological manifold. And this gives you an analytic space, which in the compact case, it really is just the unspec of the algebra of continuous functions. And let me work everywhere with complex coefficients for some reason.
Analytic of which category of
let's say C gaseous.
what?
Gaseous.
Yeah, so a different thing I could do is I could take S2 and treat it as a real analytic manifold. And again, build an analytic space over the gaseous complex numbers. Or I mean, in between here, you could think about all other possibilities like CK, C infinity, real analytic. And so now you would have here the algebra of, so what's good notation for real analytic functions?
C omega.
No, that's smooth. Oh, omega.
Yeah,
Ah,
C omega. Sometimes it's called C omega.
Yeah.
The omega. I think that's it. Thanks. And I don't know, think about all possible other algebras of like C infinity functions, CK functions in between, they would all also give analytic spaces. But then you can also like S2 is like one version of like P1 of the complex numbers. So you can also treat this as a complex analytic space. And well, then evidently you want to get something with the gaseous complex numbers. This is not affine anymore, right? I mean, there are not so many global homomorphic functions here. It is what it is. It is not affine. Let's just stay there. But it's somehow glued from two copies of unspec or holomorphic functions on a disk over convergent holomorphic functions on a disk, right? So you can cover this by two disks meeting along the circle, and similarly, this would be glued from two copies of overconvergent holomorphic functions on a disk glued along the overconvergent holomorphic functions on the circle.
And then it maps the purely topological space guy.
I think he's going to view it as a scheme first.
Okay.
So clearly, like making it more rigid, you can also now look at algebraic functions. So you can now also take P1 of C as a scheme and build something over the gaseous complex numbers. So again, this is not affine, evidently, but it's glued from two copies of the analytic spectrum of like a polynomial algebra. Or maybe I should call one T and one T inverse or whatever. And I will make a comment about this in just a second, but let me first finish. And then I can take, again, just S2 and treat it just as a condensed set. And go to base change to the gaseous complex numbers. So here I'm using the functor from 6. So basically what happens is that here you want to take the locally constant functions on S2. Well, there are none on S2, but if you secretly think of S2 as being the quotient of a profinite set by a profinite equivalence relation, which you can always do by this condensed perspective, then on those profinite coverings, you do have locally constant functions, and then you can do this gluing. So secretly, to evaluate what this is, you have to remember that secretly S2 is a quotient of a profinite set by a profinite equivalence relation, and then you can use locally constant functions. Here you have algebraic functions. Here you have holomorphic functions. Here you have real analytic functions. Here you have continuous functions. All of them give you different incarnations of what the two-sphere might be. And now there's already one really funny thing, which is something that Dustin already mentioned a couple of lectures ago. That one incarnation of the Gaga is that this is actually an isomorphism of analytic stacks. So this is one kind of Gaga statement, which is now not just a statement about some coherent sheaves or some derived category of coherent sheaves or whatever. So not just on the linear algebra, but really before you pass linear algebra, on the level of spaces, there is an isomorphism of analytic space. In particular, one of derived categories. And I mean, this is an instance where a priori the way you build these things is completely different. One is built from just polynomial algebras, one is built from algebra of homomorphic functions. And the strong Grothendieck topology that we impose is precisely there to ensure that you can have the possibility of such interesting isomorphisms. So basically, the way one proves this is that you first need to prove it's surjective. So, and this is covered by these two things. So you need to prove that those two disks together mapping to this scheme guy here, that they are a descendable map. Okay, and then you have to unravel what it means to be a descendable map and prove it.
Sorry, I have a question.
Yeah.
Yeah. Are you able to get C infinity schemes or from 6? You had 0.6 there, which I understood was schemes, but was that algebraic, or could you get other schemes like C infinity schemes?
I'm not sure what C infinity schemes are. I mean, there's this notion of derived manifolds that's somewhere in the literature.
Well, no, that's it will be generalizing manifolds, but it's not derived. But one also has derived manifolds, I guess. But I was asking the simpler C infinity scheme, so locally ring spaces that are with a local model that's a C infinity ring, which is not really an algebraic object, but you had a 6. Can you get that through 6?
Right. Well, 6 was a condensing, but I think you mean 5. Well, for this, I guess you would need to establish some relation between this notion of C infinity rings and analytic rings. And this I'm not really sure about. There is, however, in practice, some kind of functor from some suitable class of analytic rings towards C infinity rings. And that, like C infinity rings, there you want that, like for any smooth function from the real to the real or something like this, it gives you an operation on your ring. And a priori, that's not at all data that we encode in our analytic rings, because they are just a priori some, I mean, you just have additional multiplication. You don't ask that smooth functions act. But you can actually show that in some circumstances where you would expect it, smooth functions act in a unique way. Yeah. So for example, this theory here gives you a completely different way of approaching the subject of derived manifolds, because like if you just start with usual manifolds and bet into our setting, and then you can take intersections. The intersections are derived because everything is derived for us. And so you can just, if you want to work with derived manifolds, you can just use our framework. It just works. But usually there was a reason that these C infinity algebras were invented, because you needed that on these derived tensor products, you still want C infinity functions to act, which is not so clear. But you can prove that also in our framework they act. I'm not sure if this was useful information. Yeah, so the precise relation to like C infinity rings, I don't really know, and I don't really know what C infinity rings are so well. But for like the purpose of having a workable theory of like derived manifolds and so on, I think this also sits fully faithfully in our framework. Right. Yeah, maybe this is all I want to. Yeah, these are some examples. What I want to say next. Yeah, maybe one particular instance of this is like if you go from the very top to the very bottom, then those functions are just could I take as input any topological manifold, for example, or any compact Hausdorff space or something like this. And you would basically always have such a map. Maybe you should assume it's finite dimensional at some point. But other than that, you always have such a natural map from like this inclination using continuous functions to the inclination using the constant functions. But yeah, the categories of modules are very different. So up there, the category of modules, of course, just it's affine. So the modules are just modules over the algebra. C vector space was an action of the continuous functions. Whereas here, they're just chiefs of C vector space on the underlying topological space. One can show. Yeah, maybe I should actually state some of this proposition. If X is a maybe that's I don't know, locally compact Hausdorff.
The chat has a question, Peter,
Yeah.
which is why do we consider gaseous analytic ring structure on the left?
Yeah. Because otherwise, this is excluding. For example, if you want the function from complex analytic spaces towards analytic stacks, you need that somehow the intersections match up. So if you have like an intersection of compact Stein subsets in here, then the intersection is again something compact Stein. And you want this to be mirrored on the side of analytic stacks in our picture, which means that if you compute the corresponding complete tensor product of analytic rings of like homomorphic functions on D and the other disk and then tensor them together, you should get homomorphic functions over convergent homomorphic functions on S1. And this is a computation that comes out correctly in the gaseous analytic ring structure, but definitely doesn't come out for the trivial analytic ring structure, because then you would just take the usual tensor algebraic tensor product canon, and this is just some nonsense. So you need to complete the tensor product, and then it comes out right. So if X will be compact Hausdorff in finite dimensional zero sense, then you can look at the derived category of like this X, and A is any analytic ring stack, and base change it to the analytic spectrum of A. And this is just sheaves on X. Sheaves on just X, someone considers it a topological space. Those values in the derived category, derived affinity category of A. So yeah, so you can think of generally these sheaves as being some kind of quasi-coherent sheaves on an associated step. I realized that before that I should have said that the functors that take any on stack A towards P of A are also towards presentable stable infinity categories linear over D of A. So either of these are infinity categories. Satisfy descent. And hence induce functors on all analytic stacks. So for any analytic stack, you can define the derived category of quasi-coherent sheaves on X via descent. And also you can define what is like a sheaf of categories over X.
So here it is again the intermediate condition. So it satisfies descent, but for the
I mean for this funny version between descent and hyperdescent. For any. This will actually, both of these things will actually be part of some general six functor formalism, and at some point we will talk more about that. And basically our design criterion for this Grothendieck topology was actually precisely that for any analytic stack, we definitely want to be able to talk about the derived category quasi-invariant sheaves. And at some point, we also realized it's probably good to enforce the routing that we can also talk about sheaves of categories. And then we're basically taking the strongest possible Grothendieck topology where this is true.
What is PRXL?
That is the thing which is gotten by descent from the association, and spec A goes to PRL DA, which is DA modules in PRL.
Okay, which is a two.
Yeah, it's in two categories.
Okay.
Yeah, so the second thing secretly is an infinity 2 category, but we don't have to care. We can just treat it as an infinity 1 by neglecting the non-invertible homomorphism. Right. Okay, so this is some general examples that maybe we want to. I'm not sure we will like cover all of them in detail on the remaining lectures, but just want to give the general picture. But I did want to come back to the point where we started discussing analytic stacks, which was the construction of this heteroelliptic curve. And discuss this in a little more detail now. Because now we have the language of talking about this. So let me recall what we want to do. So we have this analytic ring. Plus minus 1. Yes. So this was universal. And being endowed with a topological input of unit Q. Such that when you take this usual guy, which is a free guy on a null sequence, and you tensor it up to this ring, then there is the operator that's 1 minus Q times shift. Isn't that simple? So shift is the endomorphism of P that just shifts all the integers once further. So this was this ring structure we introduced some lectures ago, and where the non-trivial computation was that you could actually compute what the underlying condensed string of this was. And it was this algebra of Laurent series in Q, which have a certain funny polynomial ghost condition on their coefficients. Let me actually let's go. and condensed string is the inner integers, and there exists some k such that
Focus.
you have the value of a and just forth into the k. Then those things. Well, maybe the underlying ring of the underlying condensed ring, because now I'm just telling you a set. Maybe I did tell you the correct condensed structure on this. Okay, so this is some funny ring of Laurent series, integral Laurent series with a rather strong condition on the growth of the coefficients. And then we recall that the goal was to define an elliptic curve. EQ over A, or really some over a triangle star. This would be a scheme such that if I take the incarnation of EQ as a scheme over A, this can be written as a quotient of a GM. I don't think version of a GM over A. Under multiplication by Q as an automorphism process. And I already, a couple of lectures back, I gave the outline of how this should go. So the first step to see that there is a certain kind of norm. And I will talk about this more in just a second, which goes from the P1 over A, but really again the P1 somehow incarnated as a scheme over A, so becoming an analytic space, towards zero infinity, which intuitively speaking, like whenever you have a point here, tells you how large it is. Having a point here is basically having a point here, so maybe mapping from A to a field or something like this, and then an element of that residue field. And so there's something like saying that on any residue field, there would be a norm.
Sending 0 to 0. It's like the absolute value.
But now this map here is really meant to be a map of analytic stacks, right? So the left-hand side is now an analytic stack. We can take the P1, we can make it, turn it into an analytic stack by this general functor. So upper is a trivial analytic ring structure, but then you can base change it to A. And maybe here I should write, I mean, so here we're incarnating this by treating it as a condensed set. And we could or could not base change it to A, yeah? And we can. But
So You have to choose some value for the absolute value of Q, like saying.
Yeah. So it should send somehow Q. Q is a section of this digital half. And it's multiplicative. In fact, there is a unique such thing. What's the property that I will mention? So it should be multiplicative in a sense I will make precise in just a second. So I want to talk about these norms. Second. 0 next to 0, 1 next to 1. Well, let me just say in the sense below. But to make it unique, I should precisely specify where Q goes. Meaning, like Q is actually a section from the analytic spectrum of A back into this, and this should go to constant half. And then you can define the analytic GM array as a subset of the P1 array. As a preimage of the open subset, sorry. The preimage of the open subset 0, infinity, and theta. And then you still have Q to the acting there. And then can take the quotient bisection of Q to the Z in analytic specs. And then by an argument I already sketched last time, this is basically a proper smooth curve. And then you have to prove the theorem, some algebraization theorem that would apply to all proper smooth curves with a section at least, that it's algebraic. So it is in the image. You also found different schemes over the underlying ring towards analytic space.
Because of the projectivity, but maybe it is one. I mean,
you need to make the line bundle, ample line bundles in the section.
Okay, it's not clear for general non-dimensional proper, even for rigid geometries.
No,
it's but here it's okay because we discussed this. So you need some Gaga and so on.
exactly.
Yeah, but we have
Need some
this,
Gaga and some Riemann rock.
or rather the vanishing of higher
Yeah,
cohomology,
exactly.
which is again part of Gaga, where is a soft server.
Well, in our approach to Gaga, you don't really get.
So your Gaga is much more general than Serre with materiality and so on. So
but it doesn't really tell you anything like Riemann rock for something you don't a priori know is algebraic. I mean, so that's kind of a separate.
Okay. Right. So one key notion that somehow comes into this is this kind of notion of norm that we want to have here. So let me actually define this in general. So let A be analytic ring. And it's a slightly awkward notion of a norm on A. That is not really a norm on the underlying set of A or anything like that, but it's rather the thing that's much more geometric. Is and that of expense. So you can take the P1. That's good. With which properties? So such that 0 maps to 0, of course. The 0 section is constant 0. The 1 section is constant 1. And then there is a multiplicativity condition. So first, let me give it one other. I want that topologically nilpotent elements have norm at most 1.
That will also follow something.
And here's how I want to phrase that. So inside the P1, I can first look at the locus A1 where I just really have just a function. But then I can look at the locus where the function is topologically nilpotent. And that is somehow given by the unspec of A. And then you join the topologically nilpotent variable. So in other words, it's again just this P treated as an algebra. So this maps to the unspec of A adjoint P, so which is an A1 over A, which maps to a P1 over A.
This is just another
Maps
name.
to zero infinity.
Is a ring.
Oh, we'll discuss this.
I'm instead of taking the next part, sorry. But I want to say that this composite factors over 0, 1.
Over the closed interval, not the half open.
The closed and closed.
Yeah, so I think that you actually want to say that it's less than 1. It turns out that the better notion is this one, for reasons I can't a priori explain, but it's the one that somehow behaves well. But I should maybe say that, for example, such a factoring here turns out to be really just a condition because there's really a monomorphism of analytic sets. And similarly for these other conditions that 0 goes to 0, then I want to say that it factors over 0 as a subset of 0 infinity. Again, that's just a condition. All right, but so these are some first properties, but then when you have a norm, you usually ask for some version of multiplicativity and also some behavior with respect to addition. Turns out we just forget about addition, but we keep the multiplicativity condition. Be multiplicative. Because I'm not working on A1 but P1, and also the image. The reason I work with P1 is actually that even on A1, I would want to allow some functions that they could have infinite norm. And if I'm allowing infinity on the target of this map, I might as well allow it on the source. But now for multiplicativity, you have to be slightly careful of treating like 0 times infinity cases. One way to do this is as follows. That x inside of P1 cubed is a closure of the locus where x, y equal to z inside EM cubed. And similarly,
This is the answer of Z, and then we put it there.
there is some actually smooth surface inside here. Similarly define some x bar inside of, we did not use x, right? Inside of 0, 1 cubed. So there's a similar thing, like on the open part, you can look at the local squared exploits. So you have an incarnation on the level of schemes of this closure, and one incarnation just some level of real numbers. And then you have x incarnated as a scheme over A maps to P1 cubed, incarnated as a scheme over A. And this maps to 0 infinity cubed. And inside here you have this x bar. And I set it vectors.
Peter, would it be the same as asking first that like the map giving the norm is equivariant for inversion on both, and then just asking for multiplicativity when you restrict to A1?
I think so. Yeah.
That was kind of the definition I thought we were using, but maybe, yeah. Well.
Yeah, but even on A1, you have to be careful that even A1 can map to 0 infinity. It could map to infinity.
Oh, sorry. I should have said that. I should have said instead of A1, I should have said the pre-image of 0.
Right. You could do that. Yeah. So it's like what happens on 0, 1 and 1 infinity is just mirror images of each other and the inversion.
Yeah.
And then on the pre-image of 0, 1, you ask for actual multiplicativity. That's, I think that's correct. Yes, I think that's correct.
The image of 0, 1 lies in A1 or not?
Yeah, it lies inside A1, yeah. Or maybe, well, because I said you're equivariant with respect to inversion on both.
Yes.
So that enforces that infinity goes to 0.
Yeah, so up there, I could, but I didn't specify that infinity should go to infinity, but it has to under the other.
Or infinity goes to, I'm sorry, infinity goes to, yeah. If you ask that it's equivariant for inversion on both sides, then infinity has to go to 0.
Did he say now that he requires infinity going to infinity?
It follows. It follows.
Why does it follow?
Because like 0 times infinity equals 1 is kind of a point in that closure. I don't know. I think it follows.
Yeah, I mean, if infinity wouldn't go to infinity, then you would run into some contradictions from this. But
and is it the
also
case
maybe I didn't carefully check it. Let me just specify it for safety.
Is it the case that the inverse image of 0, 1 lies in the A1?
Yes.
Yeah, it's not entire. I mean,
You have to show that there is no.
it's enough to show that the
The
section of
complement,
infinity,
the complement
yeah.
of A1 somehow, which is this in roughly the, well, you have to understand.
Yeah, you have to see that the complement of this of A1 is kind of generated by just the section, the infinity section in this world of analytic stacks.
Okay, so then the inverse image of the finite part of 0 infinity round lies in A1. Or not?
Right.
Ah, okay.
Yeah.
Okay. So let me explicitly say that there's no conditional on analytic.
So you don't have triangle inequality at all.
No.
Which relates to this issue that once came up that 2 might be unbounded. Like the norm of 2 could be infinite.
So you need usually the two absolute value 2 less than or equal to 2 implies.
Yeah, so I don't ask any version of triangle.
But if absolute value of 2 is less than or equal to 2, you get a triangle inequality or not? Probably. So there is a theorem that.
It does not, the absolute value of 2 can be infinite in this. There are examples, like on this gaseous analytic base. Like I will try to, in the remaining minutes, construct such a norm on the gaseous base ring. And in particular, you can then look what the norm of 2 is. And it's some function like from the analytic spectrum of A towards 0 infinity. And it's surjective. So there is some locus where the absolute value of 2 is infinite. All right. So the theorem is that I already stated on this board previously is that there is a unique norm on this gaseous space ring. Taking Q2 off. And I mean, I could have chosen any number between 0 and 1 here, and it doesn't matter which one, because you can always, because I didn't use anything about addition on the target, I can always just rescale the target by some exponential net, and it will still be in norm. All right. Yeah, I think I don't have that much time, so let me just give you an idea. And maybe just of the construction of the norm. Right. So let me start with a lemma. Let's say X is again some kind of finite dimensional locally compact hotspots. Sorry. And Y is some analytic set. Then I claim that there's some kind of Tanaka duality describing what maps from Y to X are. So it turns out that to give such a map from Y to X, it's just enough to give a functor from quasi-coherent sheaves on X towards quasi-coherent sheaves on Y with some property. But actually, you don't really need to specify the values of all. Yeah, okay, let me first say. So this is the same thing as tensor functors. Functors from there's the rough category of the being groups on sheaves of being groups on X towards E of Y. Sorry, towards X. So these should be tensor functors. Commuting with all colimits. And they should be linear over DC. Such that shriek locally on Y the following happens. So on X, you have lots of idempotent algebras. Namely, for any closed subset of X, you can take the constant sheaf on Z whenever Z in X is closed. So this becomes an idempotent algebra. It was the constant sheaf on Z.
Chad has a question.
The chat has a question.
It's about whether X is supposed to be light.
Yeah.
That is metrizable.
Yeah, metrizable, yeah.
Locally metrizable.
Let's assume X is really just contained in some finite dimensional Euclidean space. Right. So on X, any closed subset gives you an idempotent algebra, which is the one corresponding for it on Z.
He wrote whatever you need to make it work. I think he wrote nice.
This guy should be connected.
This guy should be
Connective, yeah. Non-negative homological degree.
Contained in having no higher cohomology groups, just to the left. The thing is that, I mean, if this actually was a profinite set, then this would somehow, you could basically check, I mean, any closed subset is an intersection of open and closed subsets. And so then these would be somehow just retracts of the unit. And so if Y would itself be affine, then these should of course also go to retracts of the unit object, but this is a connective object. So so if X was profinite and Y is somehow affine, then there must the images must really be connected. In general, like giving such a map, you can always do streak locally. So the condition you have to enforce should just be some streak local condition. So it turns out that this is the condition.
Shriek locally on Y, you mean the pullback or the shriek? It's the usual pullback.
Usual pullback, but shriek locally.
Shriek locally for the topology.
Yeah, yeah.
And then it remains connective after because of pullback. Okay, it's connected.
And note that the full category of sheaves on X is actually generated by these guys under colimits. So actually, to define this tensor functor, you really only have to declare these idempotent algebras. So describing maps from Y to some such guy here is completely determined by specifying for each closed subset of X, you have to specify an idempotent algebra. And if they are all already connected, then you're good to go. And the only thing you have to check somehow is that these idempotent algebras, the kind of tensor product behavior exactly matches the intersection behavior of the closed subsets of X. And that's what it means to be a tensor.
And maybe it's also nice to mention that this is actually a set, even though a priori it's an anima.
Right. Okay, we have to find some idempotent algebras. In the derived category of this P1 realized as an open space over A. And you have to, typically you have to find some that should correspond to the pre-image of like some interval from 0 to some number R, where R is data of the real number. So if you know where these pre-images should go, then because there's this compatibility on the involution, you also know where intervals should go that go from somewhere to infinity. And then everything else can somehow be written as some kind of under co-limits and intersections somehow in terms of those. So really, describing the norm, you just have to say, describe what is the pre-image of 0R, or in other words, what's the locus in here where the norm is at most R. So a disk of radius R around 0, which should be some subset of A1 over A. Which should be the analytic spectrum of some ring. A joint variable T over a guitar. And this you can just write down.
Just write down the content.
Because these should be, naively speaking, these should be certain sums n times t to the n. N greater to 0, which are somehow overconvergent, so that it should exist some r prime greater than r, so that the norm of an times r prime to the n goes to 0. Or saying it slightly differently, you would want that whenever you,
What is the norm? AN is in the integer. Okay.
well, no, the ANs are now in A.
So what is the norm?
But what you do is you can, whenever you have a null sequence in A, then you would expect that the norm stays bounded because it's bounded by 1. Or by some constant. And so to produce such a thing, you can somehow start with a case where the ANs are null sequences and then multiply by some powers of Q to make it this condition satisfied. So actually this is some co-limit of Q to the T times T.
We cannot
co-limit
say-
over some T with respect to some condition on R that I'm not able to write down. But basically, you can explicitly write down the corresponding idempotent algebra, and this
Where T is a rational
You just have
number.
to think about how you can phrase this idea in terms of the gaseous space ring. And the idea is that the absolute value of Q should be a half. So yeah, starting from the idea that you can just take any null sequence of ANs, and so there's a free algebra with a null sequence, and then multiply the ANs by suitable powers of Q to produce an algebra like that. And then there's a computation you have to do with that. If you form certain tensor products of such algebras, maybe centered at 0 and centered at infinity, then the tensor products come out in exactly the way you would hope for some of the matches the intersection behavior of intervals from 0 to infinity. So there's a computation you have to do, which really uses that you're working somewhere over the gaseous space ring, but then you can produce such a model. Maybe I should stop because I'm over time.
So, I mean, here it looks like that you have to consider the power of Q such that.
Yeah, so the T here secretly was meant to be a rational number.
Okay. So you have to make sense of this, let us say, for rational numbers, which means that when the power is divisible by something, you put the Q to this, and then you do something in between.
Yes.
I don't know.
Yeah.
Dustin will say it much better next time.
Or will I?
All right.
Okay. Very nice.
Yeah, you can ask a question.
Hi. I was wondering, is there something like an analytic space theory definition using your analytic stacks and maybe some axioms? And I'm asking because I noticed like you have different analytic spaces and their theories, and you claim that they're all analytic stacks. But if we wanted to put some, say, additional structure in an analytic space, maybe we could do this by somehow having a more general definition of analytic space using your language, as opposed to going case by case. So I don't know if did my question make sense?
Like that, it's not stacky, right? It's really more like a. I mean, you could try to restrict the kinds of gluings you allow, that they're not too stacky. But we were never happy with any of the proposed definitions that we could come up with. Dustin, do you have a better answer?
I didn't quite understand the question. So
like you're saying, there are some examples. So I don't know, I came here a bit late. So someone said there was adic spaces that someone showed not someone, Peter showed that they're analytic stacks, and then complex analytic spaces, and then somehow if you restrict to real analytic, you get real analytic spaces.
okay, yeah.
Okay, so it seems all like I understand they have different theories.
Okay,
Like,
yeah.
So my question is, can you define analytic space theory using your language? Because if I wanted to put an additional structure in an analytic space, perhaps I want a general definition for all analytic spaces.
But
And put the structure there.
that's exactly what we're doing. That's what the analytic stack is.
So you can say, I have an analytic space theory, and this reduces to each known case. So
Well, I mean, I don't know.
Analytic stacks are such analytic space.
define analytic space theory?
I don't know what, actually, I have to know what you mean by that.
I don't know what I mean.
Yeah.
I mean like something that would generalize all the.
Yeah, that's what we're trying to do with this concept of analytic stack. Yes, you shouldn't be scared of, you shouldn't be put off by the fact that we changed the name from space to stack. That's basically a technicality, but that's the goal.
But
So you have a definition like an analytic space is an analytic stack that. Blah, blah,
Well, you
blah.
could try, yeah, you could, for
Maybe we
example,
have some open.
Yeah, that's my
some
question.
kind of
Like, do you have a
open-
definition like an analytic space is an analytic stack satisfying some axioms? Do you have this?
Well, we have too many, maybe.
Well, what I mean is like, do you have the an ultimate one? Kind of like the umbrella one from.
we tried, but we could never
I mean, you could just say that the functor of points takes values in sets.
No,
But
you can't.
it
Because
No,
then
but
even,
can you have
then
just
even affine ones are not okay.
Sorry,
kind of
what?
Open, Zariski open.
If you ask that it takes values in sets, then even affine analytic stacks are not fine.
So
Well,
anyway,
yeah, but the classical ones are, so.
anyway, in
No,
the classical,
no, the affine line like takes a ring to its underlying. Like because
Okay.
the test category consists of derived things, you can.
Yeah. That's true. That's true.
no, but
Okay.
anyway,
So you don't have a definition of analytic.
But I mean, you could ask that it's a colimit of affines along monomorphisms. That's the condition.
Sorry, what's the condition?
You could ask that it's a colimit of affines along monomorphisms.
Okay, thanks.